You ever thought much about crystals? They're in the granite countertops that we have, they're the gems that we wear, they're really all around us. I want to talk specifically today about crystals from pegmatites. So pegmatite means big crystals. I actually have a piece of one here, which shows a big tourmaline crystal here, as well as some lepidolite and some quartz crystals in here. So pegmatites come in all sizes, from small veins to as big as a house. And I specifically want to look at quartz crystals in pegmatites, much like this, which shows some quite large ones. And I want to ask you the question, how long do you think it takes for this crystal to grow? I want to talk specifically today about the Stewart pegmatite, which is pictured here in the background with another large tourmaline, and we're going to look at the quartz crystals there. I also want you to pay attention throughout this video to the small crystal growing up in the corner. So let's get into the Stewart pegmatite. So here is a schematic of the Stewart pegmatite, and in the bottom left corner here, we have a person for scale. We go to the center here, we have a core area, since this is a layered pegmatite, which is full of lithium-bearing minerals like lepidolite, which I showed you, purple here. And generally, though, it's granitic in composition, so it's albite and other feldspar and quartz throughout the thing. So what specifically we're going to look at are these chimneys, which have the quartz crystals, and they're fairly late stage. After most of the pegmatite is crystallized, except for the core zone, these tend to pop up into the other spots. So let's talk about the quartz crystals from there. This is one in particular, which has been imaged using cathodoluminescence, which is a technique that uses electrons to discern where defects are, and different defects come as different colors. So much like this white, the orange, and the purple. We're going to continue to talk about those colors throughout the talk, but with this as a reference, so this white, this orange, and this purple. These red lines here indicate growth. Next, let's talk about the trace element content of this quartz crystal along this A to A prime transect. So what we see for trace elements are concentrations along the y-axis here of germanium, lithium, aluminum, and titanium. And then distance, just like the A to A prime like we talked about before. So what we see as we go along is germanium tends to fall, while lithium and aluminum tend to rise at this white to orange boundary, and generally tend to increase through the rest of it with these small inclusions. Well, interestingly, this is not a flat profile throughout the crystal. When we look at the isotope ratios, we see something similar, where we see a general increase throughout. I should mention that this axis is the delta 7 lithium value, which is the lithium 7 over lithium 6 ratio, and once again versus distance. So how does this compare to other systems? Well, when we look at the trace elements, when we look at these equilibrium whole rock data for granites and pegmatites, we see the granites tend to be higher in titanium, and the pegmatites also tend to be lower in aluminum. So we see values that are much higher than what we'd expect for equilibrium. With the lithium isotope ratios, we see something similar, where once this isotope ratio on the bottom, for our 3 different crystals, we see for the range out of equilibrium with, say, granites, and one in particular that's even beyond equilibrium of any other system, seawater or marine pore water or anything for that matter. So that leads us to believe that these systems are seeing, that the specific pegmatite is seeing some kinetic effects going on. So how can we determine crystal growth rate, which is a kinetic effect, from these trace element contents? To explain that, I have an animation here. So what we have is concentration versus distance. And as a crystal grows, it will change the concentration that's uptaken of these trace elements. I'm going to plot incompatible elements and compatible ones. Incompatible meaning it doesn't like going into the crystal, whereas compatible likes going into the crystal. We start at a constant concentration, and then we will see a dashed line moving across from left to right, and that is the crystal interface actually moving. And so on the right is the liquids, on the left is the solid. Let's watch it. So as it starts, we see that the compatible elements fall, and the incompatible rise, and they both tend towards a steady state. Let it finish. And when we look at the liquid side, on the other hand, so I'll run it again, we see this drastic increase in incompatible and this fall in compatible. The reason this occurs is as the crystal moves, the incompatible don't want to go in. So they get concentrated at the interface. They get pushed up against it, whereas compatible gets sucked in, kind of like a vacuum. And this ends up causing this profile that we see. And eventually, because this is a diffusive process going on in the liquid, we eventually, crystal growth rate and diffusion balance each other out, giving us a steady state. So to use that, we can look at we'll look at actual data, which are these dots, compared to these models, which are growth rate models. This is concentration versus distance for germanium, which is a compatible element in quartz. And what we see, if we change the growth rate from a slow one to a fast one, is this the models tend to capture a fair amount of the data between this blue and this red. If we look at aluminum, which is an incompatible element, there are some inclusions in here which make things a little more difficult. But once again, going from slower growth rate to a faster, we have this increase, which is what we were seeing for incompatible elements. And once again, blue and red can capture some of the data. What do those numbers mean? Well, so for this crystal, the white area would have grown at 10 to 100 millimeters per day, and the orange at 1 to 10 meters per day. This goes with a less than 3-hour growth time for the white area and a less than 4-minute growth time, so much faster for the orange, which means the total crystal, except for the purple, could have grown in 3 to 4 hours, say. The purple area is harder to figure out a growth rate for because our model only works if we've gotten back to a steady state, which we haven't yet. Now, how do these rates compare to other processes? So what we have here is time to grow 1 centimeter, or move, because these are rates of movement, whereas these are growth rates up here. And if we look at volcanic quartz compared to ours, which is red, we see that we're a little bit faster than that, but at the low end, but much faster at the fast end. But interestingly, we're actually similar to grass at the low end, but faster than even the growth of grass. And then if we look at, say, slow slip, we see that the quartz rate is similar to some of these slip rates. So that means that some growth rate may actually, crystal growth may actually matter for some of these systems. Now remember, I told you to pay attention to that crystal up in the corner. Here's why. So if we grow throughout this entire video at the rate, at the fastest rate that we'd expect, this is how big our crystal would have gotten by now. So hopefully that helps you understand just how fast these things can actually be. Thank you for listening.